Welcome back, deep divers. Today, we're going on a journey to the center of an atom, to the nucleus.
We're going to unpack a ton of knowledge about this tiny structure that has huge implications for, well, pretty much everything.
Whether you're here to brush up on some chemistry or maybe you're fascinated by nuclear energy, we've got something for everyone.
We'll start with the basics, of course.
Yeah, the Nucleus 101, but we'll also be diving into some really mind-blowing stuff. So imagine the atom is like a bustling city.
Okay, I'm picturing it.
The nucleus is the city center, right? It's packed with these particles, protons with a positive charge and neutrons, no charge.
Right, and it's unbelievably dense in there. Most of the atom's mass is crammed into that tiny nucleus.
And the number of protons, that's the key. That's what determines what element the atom is.
Exactly. One proton, you got hydrogen. 6 protons, that's carbon. The proton count is like the atom's ID card.
Now, what about the neutrons? They're just kind of hanging out in there, right?
Well, not exactly. They're crucial for stability. See, all those protons packed together, they're all positively charged.
So they want to push each other away.
Exactly, like magnets repelling each other. But there's this incredible force holding them together. The strong nuclear force.
One of the fundamental forces of the universe, right?
Right, and at these tiny distances, it's insanely powerful. Like, think superglue times a million.
Okay, so we've got this super dense nucleus held together by this mind-blowingly strong force. But things aren't always peaceful in there, are they?
Yep, not always. Some nuclei are unstable.
What does that mean, unstable?
They undergo radioactive decay. Basically, they emit radiation, and over time, they actually transform into different elements.
Whoa, so the atom is like changing its identity.
Yeah, it's like an atomic makeover. And this process, radioactive decay, it's the basis for a lot of cool stuff.
Like what?
Well, like carbon dating, for example.
Oh, yeah, for figuring out how old ancient things are, right?
Exactly. We use the decay of a radioactive isotope of carbon, carbon-14, to measure how long ago something lived.
So this seemingly abstract concept has some really practical applications. What else?
Well, radioactive isotopes are also used in medicine, you know? In radiation therapy, they target and destroy cancer cells.
Wow, so this tiny nucleus is impacting our lives in ways we might not even realize. Speaking of impact, what about nuclear energy?
Ah, yes. Nuclear energy. When we talk about that, we're talking about 2 processes, fission and fusion.
Break those down for us.
Okay. Fission is like splitting a heavy nucleus, like uranium, into smaller pieces. And that releases a ton of energy.
That's what powers nuclear power plants.
Right. Exactly. And fusion is the opposite, combining light nuclei, like hydrogen, to make a heavier one.
And that also releases energy.
Oh, yeah. A massive amount.
Yeah.
That's what powers the sun.
So the sun is like a giant fusion reactor in space.
Basically, yeah.
Yeah.
But to really understand how these processes work, we need to dive into some models that scientists have developed.
Models, like blueprints for the nucleus.
Kind of. One is called the liquid drop model. It pictures the nucleus as a drop of liquid, with protons and neutrons jostling around.
I can kind of picture that.
And then there's the shell model. It's more like the protons and neutrons occupy specific energy levels, or shells, within the nucleus.
So like electrons orbiting the nucleus in shells, the protons and neutrons also have their own shell structure.
Exactly. And how these nucleons are arranged in the shells affects the atom's stability. We're getting into really cool stuff here.
Yeah, this is where it starts to get a little, well, mind-bending. Almost like we're entering a world where the rules of physics don't apply.
Well, you're not wrong. We're starting to talk about quantum mechanics.
Oh, boy.
For example, there's quantum tunneling, where particles can pass through energy barriers they shouldn't be able to.
Wait, what? Like walking through a wall?
It's crazy, I know. But at the quantum level, particles behave like waves. Those waves can kind of leak through barriers.
So we have to rethink how we picture these particles, right? Not just tiny balls, but waves that can do weird things.
Right. And this quantum tunneling, it's crucial for nuclear fusion. Like in the sun, protons need to overcome their repulsion to fuse. Quantum tunneling helps them do that.
Okay, my mind is officially blown. So we've got these protons and neutrons behaving like waves, held together by this super strong force, all in this incredibly dense nucleus. It's like a tiny universe in there.
It really is. And we've only just scratched the surface.
Well, I'm definitely hooked. What's next? Where do we go from here?
Well, next we're going to explore this concept called binding energy. It's basically the glue that holds the nucleus together.
All right, let's dive in.
Binding energy. It's basically the amount of energy you'd need to completely take apart a nucleus, like separate all its protons and neutrons.
Okay, so it's a measure of how tightly those particles are bound together.
Exactly. And here's the key. The higher the binding energy, the more stable that nucleus is.
Makes sense. A nucleus with a high binding energy, it's not going to fall apart easily.
Right. And some nuclei, like iron-56 and nickel-62, they're the champs. They have the highest binding energies, making them super stable.
So they're like the Fort Knox of the atomic world.
Yeah, I like that analogy. And their stability, it actually has huge implications for the whole universe.
Okay, now I'm really intrigued. Tell me more.
Well, think about fusion, right? When lighter elements fuse into heavier ones, like in stars, that releases energy.
Because the heavier nuclei have higher binding energies.
Exactly. So stars are basically giant fusion reactors powered by this quest for higher binding energy.
Wow, that's amazing. And when massive stars explode as supernovae.
They create even heavier elements, spreading them out into the universe. So we're talking about processes that shape the very elements that make up, well, us.
I know, it's mind-blowing. But binding energy isn't just about stars and supernovae, right? You mentioned it has applications closer to home.
Yeah. Like, have you ever had an MRI scan?
Sure, who hasn't? It's
Oh.
like they use magnets and radio waves to see inside your body.
Right. Well, the principle behind MRI, it's called nuclear magnetic resonance. And it's based on how atomic nuclei behave in a magnetic field.
So the binding energy of the nuclei affects how they respond to the magnet.
Exactly. Doctors can analyze the signals from those nuclei to create those incredible images. Helps them diagnose all sorts of medical conditions.
This is incredible. We started with this tiny nucleus, and now we're talking stars, supernovae, and MRI scans.
Right. It all connects. That's the beauty of science.
So where do we go from here? We've explored the structure, the forces, binding energy, even quantum mechanics. What other secrets are hiding in the nucleus?
Well, remember how we said protons and neutrons are found inside the nucleus?
Yeah, they're like the building blocks.
Turns out those building blocks, they have their own building blocks.
Wait, what? What do you mean?
Protons and neutrons, they're made of even smaller particles called quarks.
There's a whole other level inside protons and neutrons.
Yep. And the forces that hold those quarks together, they're even stronger than the strong nuclear force.
Okay, now we're getting really deep. Tell me about these quarks.
Well, quarks come in different flavors, and they have this property called color charge.
Color charge, so they're like red, blue, green.
It's not actual color like what we see. It's more like a label that describes how they interact.
Oh, okay, so it's like a code.
Exactly. And the force that binds them, it's carried by particles called gluons.
Gluons, like the glue that holds the quarks together.
Yep. And the study of all this, quarks, gluons, the strong force, it's called quantum chromodynamics.
Quantum chromodynamics, that sounds intense.
It is, but it's fascinating. It's helping us understand matter at the most fundamental level.
So how do scientists even study these quarks and gluons? They're so tiny.
They use these massive machines called particle accelerators, like the Large Hadron Collider.
I've heard of that. It's like they smash particles together at super high speeds.
Right, it's like recreating the Big Bang in a lab. By studying the debris from those collisions, they learned about quarks, gluons, all sorts of fundamental particles.
That's incredible. It feels like we're pushing the boundaries of human knowledge.
We are. And who knows what else we'll discover. The nucleus is full of surprises.
I'm sure it is. But before we go even deeper down this rabbit hole, let's zoom out a bit. What about the practical applications of all this nuclear science, beyond what we've talked about already?
Well, radioactive isotopes, for example, they're used in all sorts of fields, from agriculture to industry.
Oh, like how? Give me some examples.
In agriculture, you can use them to track how plants take up nutrients. Helps farmers optimize fertilizer use and improve crop yields.
So it's like giving plants a checkup, seeing what they need.
Exactly. And in industry, you can use isotopes to gauge the thickness of materials or detect leaks in pipelines.
Wow, it's like X-ray vision for industrial processes. What else?
Well, of course, we can't forget about nuclear power. It's still a major energy source in many parts of the world.
Right, using fission to generate electricity. And it's a cleaner alternative to fossil fuels.
Exactly. Of course, there are challenges, like dealing with nuclear waste, but it's still a vital part of our energy mix.
And I've heard scientists are developing new, safer reactor designs.
Yeah, there are some promising advancements. Molten salt reactors, small modular reactors, they could be game changers in terms of safety and efficiency.
It's exciting to think about how nuclear science could help address some of our biggest challenges, like climate change.
It has huge potential, but it also comes with big responsibility.
Definitely. We need to make sure nuclear technology is used safely and responsibly.
Absolutely. International cooperation, strong regulations, public engagement, those are all key.
It's complex, but it's a conversation we need to have, harnessing the power of the atom for good.
Well said. And as we continue to explore the nucleus, its fundamental properties and its applications, we need to remember, knowledge is power, but it's also a responsibility.
I love that. A perfect segue to our final thoughts. We've covered a lot of ground today. From the basic structure to, wow, quantum chromodynamics. What are some key takeaways for our listeners as we wrap up this deep dive?
Well, I think the biggest thing is the nucleus, even though it's tiny, it plays a huge role in our understanding of the universe and our place in it,
It's like a reminder that even the smallest things can have a massive impact.
and that the journey of scientific discovery never ends. There's always more to learn, more to uncover.
So what questions are you left with after our exploration today? What aspects of this tiny but mighty structure are you most curious about?
It's pretty amazing to think about, right? We started with this tiny nucleus, so small we can't even picture it, and we ended up talking about like stars and the birth of elements.
Yeah, quantum mechanics and all these incredible forces at play.
It really shows you how everything's connected in science. The nucleus isn't just some isolated thing. It's tied to like astronomy and biology and medicine, even energy production. It's a truly interdisciplinary field. And who knows what we'll discover next, right? As we keep digging deeper into the nucleus.
I mean, imagine a world powered by fusion energy, clean, safe energy, just like the stars.
That would be incredible. Or figuring out how to safely deal with nuclear waste. That would be a huge breakthrough for nuclear power.
And what about new medical treatments, new ways to diagnose diseases, all thanks to our understanding of the nucleus? The possibilities seem endless.
They really do. But we have to remember, as we explore this powerful science, we need to be careful, responsible.
Absolutely. We need to talk about the ethical side of nuclear technology, make sure it's used for good, for the benefit of everyone and the planet.
That's where educating people comes in. The more we understand about the nucleus, the better decisions we can make about how to use it.
Well said. So as we wrap up this deep dive into the nucleus, I hope you're leaving with a sense of wonder, a thirst for knowledge, and a new appreciation for this tiny but powerful structure that's at the heart of, well, everything.
Yeah, and remember, this isn't the end of the journey. We've got some great resources in the show notes if you want to keep exploring.
So keep those questions coming. Stay curious. You never know, maybe you'll be the one to make the next big discovery in nuclear science.
Thanks for joining us on the Deep Dive.